This lecture is going to go over the chemistry tests that we'll be doing, and we'll make sure we explain them so we understand what it is we have going on. And this is consistent with the Friends of the Chicago River, a professional organization, to see to it that the waterways of the Chicago River, including the Middle Fork River of the North Branch, is maintained in a healthy ecosystem. The first topic is going to be turbidity. Turbidity is pretty much how dirty or murky the water is. Here you can see very, very turbid water, and this is actually much cleaner water, and you just see this turbidity flow moving out. This is generally a river that meets kind of an ocean or a lake. This happens to be an ocean here. But the importance: dirty water impedes breathing of animals with gills, impedes filter feeders, impedes sunlight that leads to a reduction in photosynthesis. The sources of turbidity: sediment and organic debris suspended in moving water. Now, you'll see that the turbidity itself is going to change based on the speed of the water itself. That faster water has more kinetic energy. Well, the more kinetic energy, the more turbidity, the more sediment that the moving water can carry. The second factor we're going to look at is temperature. And we're going to be comparing, we won't have much of a temperature difference, so this won't be a major issue here. But the importance: too high of a value will preclude cold water animals from living in the river. Less oxygen can dissolve in the water with higher temperatures. Higher temperatures also promote higher growth rates, generally of microbes and algae. The sources of temperatures: hot water discharges, particularly power plants, and the lack of shade. So what we're looking at here is we're looking at these temperature ranges. When the temperatures continue to increase, you change the conditions that biota can live within. So microbes, even microorganisms and insects that are kind of the basis of the food chain, are unable to live in warmer water temperatures. Cooler water, generally, you're going to get a healthier environment. And temperature, we're going to find out, is going to be a factor of dissolved oxygen. Dissolved oxygen is temperature dependent. Warmer water can hold less dissolved oxygen. Colder or cooler water can hold more. Another feature: pH. The importance: this indicates the number of free hydrogen ions in the water, and it's logarithmic. So too high or too alkaline, or too low, acidic, these values would then preclude many life forms from living in the water. So there's kind of a really healthy value, and that is going to be somewhere around a pH of 7. The sources: acid rain, mining. Note that a lower pH is buffered by the presence of limestone in the bedrock of an area. So pH can actually be buffered, right, kind of stabilizing it. So what happens when we start looking at values? Well, if you have too low of values, you stress aquatic life very, very dramatically. But you get this very nice range that's considered suitable for most aquatic animals, and that definitely includes the 6.5 to 8.5 range. So we're looking at pretty much in this range right here. But it's not a large range. Instead, it's a range that actually just makes it healthier or available for healthier conditions. Another characteristic or parameter is dissolved oxygen. This is the oxygen that's breathed by aquatic animals. The sources: these are byproducts of photosynthesis. They are mixed in from the air when water is turbulent. For example, in riffles. Riffles are good in the Middle Fork River because it churns up the water, it increases the surface area, and therefore more dissolved oxygen, more dissolved atmospheric oxygen, can make its way into the water itself. So let's look at the values that you have. When you have low dissolved oxygen values, you're really limiting what can survive, what can live in a waterway. But when you start getting into healthier levels, we're really talking about higher levels. So there's an optimal value, and we can compare the dissolved oxygen values here. Too much of something is not necessarily a good thing. So we'll be looking at dissolved oxygen. We need to make sure that you realize that dissolved oxygen is by far and away the most important factor of the parameters for a river's health. Nitrates, another factor. The importance: this promotes growth, and excessive levels can lead to eutrophication and fish kills and the reduction in biodiversity. The source of fertilizers. So some of the values here that we can look at is, and you might be surprised, there are times of the year where we have much higher values, right? If we just recently fertilize the fields and there's a heavy rainfall, a lot of that fertilizer makes its way into the waterways. So if we look here, excess nitrate can lead to eutrophication, or what we call algal blooms or algae blooms themselves. Another parameter: phosphate. This promotes growth also. generally in algae and microbes. Excessive levels can lead to eutrophication also, and fish kills and the reduction of biodiversity. The sources of phosphate, fertilizers also, but also including soaps and detergents. So these values here are much like that, similar to that of nitrate. They can actually lead to this eutrophication in algae or algal blooms themselves. And you can see here you get this top layer film of this green muck. That would be considered eutrophication of this particular waterway. So what is eutrophication? Well, let's look here. Once you get this runoff, right? Runoff is the water that's going to be picking up the fertilizer, the sediment, could be from soaps and detergents. You get nitrate and phosphate in the water. They're going to promote bacterial and algae growth. So bacteria that then begin breaking down the algae, they use up the oxygen in the water. Well, as they die, decomposition begins to take place. And what happens is you get this system that's completely consuming all of the dissolved oxygen in the water. So eutrophication leads to a decrease in the health of this particular body of water. So eutrophication is the result of algal blooms or algae blooms, where algae creates a surface layer blocking out sunlight penetration. As a result, the dying and decomposing algae sink to the bottom of the water. Decomposition takes more of the available dissolved oxygen. So not only are you creating this layer of film at the top to where you're impeding sunlight making its way in, right? Because photosynthesis is going to then, these plants are going to then be putting back dissolved oxygen as a byproduct of photosynthesis itself. You're actually creating this three-way system of not allowing dissolved oxygen into the water, thus decreasing the overall health of this water. Another factor that we're not going to study, so I'm just going to graze over, is called BOD, biological oxygen demand. It's essentially how much oxygen is breathed by aquatic animals. It's what remains after several days of bacterial decomposition. And we can look at this as a factor of living organisms need dissolved oxygen, and if it's not available, they cannot survive, at least not in a healthy environment. Another factor is total dissolved solids. This is not one we are going to calculate. This actually impedes life processes of animal guilds, right? The dissolved solids. It's a kind of a way of looking at turbidity, but it's a little different. This is all of the stuff that's in there. And this can actually impede sunlight, and it can get in the way of photosynthetic and other organisms that live in the water, and it decreases the overall health. And last factor we'll look at, or feature, of the 9 parameters that exist. Fecal coliform. Fecal coliforms are bacteria that are, though not always pathogenic, they are indicators for the presence of human feces and thus the potential for the presence of pathogens. So the sources are septic systems that leak. We can talk about combined sewer overflows, and we'll be looking at that when water is not cleaned. It's actually just spilled directly back into waterways, Lake Michigan, Chicago River, North branches of the Chicago River, including the Middle Fork. So there are certain values that the EPA, the Environmental Protection Agency, has for safe swimming levels. So it's 200 colonies per 100 milliliters. And there are values that are safe for boating as well, and that's 1,000 colonies per 100 mLs. But fecal coliform are very much a part of waterways. There can be low levels that are considered to be healthy or more healthy than others, and then the higher the value, the less healthy. So here are the tests we'll be looking at. We're not going to do all of these, but we will be doing 6 of them. We'll be looking at pH, phosphate, nitrate, dissolved oxygen, change in temperature, and turbidity. These are the 6 parameters that we will look at in this class. And there are some expected ranges, and these are provided for you. And we'll be talking about the units of measurement in class. And notice that there are certain values. Some we want higher, some we want lower. But it's a combination of these parameters that make a body of water healthy. And finally, we're going to be looking at Q values. These are Q value charts. We're going to be taking our data, and in your binder you'll see that you have cleaner versions. I just wanted to get them all on here so that we could talk about them and look at them within the screencast. But in this case here, when we look at Q value charts, we need to make sure we understand what a Q value is. A Q value is a way of standardizing all the different water quality test results so they can be combined and used to find an overall water quality value. You can think of Q values like a score on a test. Less than 50 is a failing grade, whereas 90 or more is like an A. You're going to use the following Q value charts for each of the water quality tests that we perform. Remember, we're only doing 6 of these. So we are going to be able to collect data and analyze it statistically and determine what these values are and we'll put it together to determine what's called the overall water quality. Now, some locations will call it quality. I don't like that word, but once again, a 90 to 100% is considered excellent. 70 to 89%, a little larger range, is considered good. 50 to 69% is considered medium. 25 to 49 is bad, and 0 to 24 is very bad. Just like a student earning a grade, the higher overall water quality, the better the health of a river stream system. So the above table is how we will take numbers to make sense of the comprehensive qualitative explanation of a water's health.